I did problem 27 from chapter 14, subsection 3. It's a problem in which we're going to be converting from Cartesian coordinates to polar coordinates. Now, what made this problem interesting to me, and the reason that I chose it, is because it's a problem where we're going to be combining the sum of two iterated integrals into a single iterated integral, which we will then have in terms of polar coordinates. So, with these problems, we've only done a couple of them. I think there was one on one of our homework assignments, and then there's a couple in the book. But we haven't really been exposed to too many of these. So I find it useful to draw them out. To do that, since we're going to be integrating over two different regions in this first part, I like to look at what they look like combined. So this is the first region that we're going to be integrating over if we were to do it without conversion to polar coordinates, which is not really something that I'd want to try and do, but this is the region that we would be integrating over right here. So the way that we're getting that is the boundaries for y are going to be 0 and y equals x, and the boundaries for x are going to be 0 and 2. So that gives us this nice little triangle here. Next step is going to be to find the region that this is going to be integrating over, and then sketch that out. So I've done that in the same graph. So this is the two combined now. We've got that same triangle we were just looking at, and then we've added in this little purple sliver here. Now that sliver is bound by 0 for y, and then the other boundary for this is going to be root 8 minus x squared. This root 8 minus x squared is what's really making the polar coordinates possible and easy. It's giving us that circle, not full circle since we're only taking a section of it, but that circle that makes the polar coordinates more relevant. So again, that boundary is right here. It's kind of this orange all the way around here, but the relevant section is just right this area right here. Then the boundaries for x are going to be 2, so that comes up right where we left off, 0 through 2, 2 through, and then the other boundary is 2 root 2. So it's 2 through 2 root 2. Now the 2 root 2 is also where this function is going to come down. That's usually the case. Usually you've got one boundary where, well, actually both boundaries are going to intersect here on all four areas. But this one right here is what's going to give us our radius. So that's kind of important. Now that we've got this graph, can kind of simplify the graph, I guess. And this right here gives us our relevant information for converting this graph into a single iterated integral in polar coordinates. So instead of the two regions with the, I guess, 4 sets of boundaries that we had with the sum, we now have one region with 2 sets of boundaries. Those sets of boundaries being, with respect to r, from 0 to r equals 2 root 2, and with respect to theta, from 0 to pi over 4, since we're going counterclockwise in terms of the bounds. So once we get that, we can turn it all into this right here. So again, we've got the 2 sets of boundaries that I just went over, and then we've got this right here, the function that we were previously integrating in terms of r. So when we're converting to polar coordinates and we have x squared plus y squared, we can always turn that into r squared. That's of course because r squared cosine theta plus r squared sine theta will simplify down to just r squared. So if we didn't have something simple like this that would cancel out, we'd have to remember that x is going to be r cosine theta and y is going to be r sine theta. then since we are converting to polar coordinates, we also have to bring in this r right here. So whatever you get, just slap it on that extra r, which a lot of times is actually pretty helpful, since we are going to have circumstances where we have these root r squared, or not root r squared, but root r functions or situations. Sometimes it'll be like root 8 plus r squared or something. That's going to be a lot easier to deal with this extra r over here. So there has been at least 2 or 3 examples I remember where it would have been a lot more difficult if it wasn't for the fact that we are bringing in that extra r when we convert to polar coordinates. Then from here it's pretty easy. We can simplify this down a little bit, and in doing so we get this right here. And then all we have to do is integrate. That's the easy part. So when we integrate with respect to r, we're going to get this. And we just evaluate that. And we get this right here. Then we want to integrate with respect to theta. That gives us this. So again, it's a pretty simple integration. All we're doing is integrating a constant with respect to theta. And once we evaluate that, we get our answer. So our answer is going to be right here. It's 4 root 2 pi over 3. It's not too clean, but it's not too bad either. So I know I went over this integration kind of quickly, but that's not really the difficult part in this problem. The real meat of it comes in evaluating the sum down, or converting the sum rather, to polar coordinates. So the graph and then this part right here. So hopefully that was helpful, and I hope you enjoyed it. Okay, bye.